22,000 years ago, a meteorite weighing millions of tons crashed into the Earth and left this. The Barringer crater in Arizona, over 1 kilometer across and about 200 meters deep. It's the result of just one of the innumerable impacts the Earth's surface has suffered throughout its history. Impact cratering is now recognized as a fundamental geological process throughout the solar system.
Way back in the 1860s, 1870s, there was a big debate on whether or not craters were formed by volcanic processes or by impact processes. Ironically, one of the gentlemen, a guy named Proctor, who was sort of the Carl Sagan of that day, proposed that it was an impact process was the dominant thing that was affecting the moon. By the time he died in the late 19th century, he had reneged that hypothesis and went to the volcanic idea. It wasn't until the late 19th century when Gilbert proposed these things might be impact craters based on some simple stratigraphic relationships that became the undercurrent of what the dominant process. Ironically, still the astronomers believe that they were volcanic and the geologists tend to believe that they were impact.
But it was the advent of the nuclear bomb and other high-energy chemical explosive devices that finally decided the issue. In such explosions, it is shock waves that are responsible for the ejection of material, and not just the rapid expansion of gas. Because of this, the distribution of ejecta around shock wave craters is quite different from that around volcanic craters. So the Arizona crater was formed by a shock wave event, and not volcanism. By detailed study of well-preserved craters such as this, we have learnt much about the mechanics of impact cratering. And by studying impact craters on other planetary bodies, we can learn more about the history and origin of the solar system. There are other ways of studying impact events. At Moffett Field, south of San Francisco, scientists have been researching into the details of crater formation by firing projectiles at high velocity down a barrel into a bucket of sand set on the floor of an evacuated chamber.
We can produce a hole in the ground, we can produce it with a very small object. A quarter-inch ball might produce a 20-inch diameter crater. It'll look conical in shape, but that won't be necessarily what a lunar impact crater will look like. Here's an example of a lunar crater, and to give you an idea of scale, the meteor crater, the Barringer crater in Arizona, would probably be about the size of this crater right here. This gives you an idea of the amount of energy that's involved when one of these events actually happens. It's a catastrophic process that is very difficult to imagine, and these experiments provide us only sort of a small glimpse of really what's going on.
In this shot, a thin layer of red tempera has been spread over the surface of the target so that the trajectories of particles in the surface layer can be followed in detail. The chamber must then be evacuated slowly to avoid the danger of mini volcanoes in the target. An electronic control system will fire the gun, having first switched on 3 high-speed cameras and their lights to record the impact in slow motion.
Well, I hope it works.
I hope so.
Any bets?
No.
If it works, I'll get you a donut.
Oh, if it doesn't, I gotta give you one.
That's right.
I'll get you one with the hole.
Every time you do one of these things, it's a little bit different. I don't know, it's sort of like opening a present. You never know what exactly is going to happen, especially when you take perhaps a day preparing a target, and then suddenly to have it work. I feel like I owe you a donut, Joe. Can you make the coffee?
I'll make the coffee.
I'll bring the donut.
All right.
And then the next part of the anguish is waiting for those films to come back so we can look at them and find out if anything unusual has happened. And I'm constantly surprised. This is what's the beauty of doing experiments. You never know what's going to happen next.
Heavy.
Ah, great. That's great. Okay, that did just what we expected. You can see where the red material went out the fastest and the farthest. It's plastered against the outer wall. And the red material was the stuff that was on the surface. The white material that was from underneath is all around the crater itself. It's not really a bowl-shaped crater, it's more of a conical-shaped crater. And the projectile that was an aluminum ball has, if we could dig it out, would be actually a squashed ball. At higher velocities, the ball would break into many small pieces, in fact will melt. And at even higher velocities than that are characteristic of craters that are on the moon, it would be vaporized and melted completely, and it would melt a great deal of the target. As a result, the crater that we have here in many ways looks like some of the smaller craters that we see on the moon, but it doesn't reproduce exactly what we find there. Here we can see where the red temper that we had on the surface of the target has been covered by the lighter material that was below it. And you can see the decay and eventually that of the thickness of that ejecta, and eventually it gives out about here where it predominantly becomes red. And as you go farther out, you can see just primarily red clumps that have impacted. And these would have produced secondary craters had they been formed on the moon at a much larger scale.
And this is what the cameras recorded. An impact slowed down to 1/16 its normal speed. What do such pictures tell us?
One of the things that we can tell out of these experiments is that the process of cratering is a very orderly process. It's not this chaotic jumble that you might envision by looking at an old war movie or looking at the nuclear explosion. It looks very like a chaotic jumble, a cloud. Instead, in a vacuum condition, which we have for the moon, it forms a nice series of conical shape, inverted cones that marches outward. And as it marches outward, it doesn't change its form very much. And this marching outward is a result of the locus of ejecta material coming from the inside first and at the highest velocities and contributing to the top of the ejecta plume. The material that is down at the bottom of the plume is coming from deeper in the crater. And even after the crater is formed, this ejecta curtain simply keeps on marching outward in a beautiful, regimented way. And that's in contrast to what happens if we introduce the effect of an atmosphere. And here we find that the beautiful, symmetrical, even transparent ejecta curtain that marches outward is replaced by a much more complex curtain. We find that the material seems to be drawn in at the top and bulges out at the base. It's a very fundamental difference between impact in a vacuum and impact in an atmospheric environment. The net effect is that we can produce very strange-looking craters. They're strange in comparison to the moon, but they're dead ringers for many of the craters on Mars. And by varying the atmospheric pressure, increasing it, decreasing it, we can go through and look at almost all the various morphologies that we see. Now, here we've taken two photographs, cut them in two, and then pieced them together. The right photograph is of Mars. The left photograph is of a crater that we produced in the laboratory. And we see that they're very similar. This is in a completely anhydrous environment without water. And we find that we form this ridge. And this ridge continues around and at about the same distance that we find for the Martian craters. We believe this ridge is produced by the dynamic motion of the atmosphere in response to the cratering event. It's that curled and that bowed ejecta curtain that we see. And behind that ejecta curtain, this is sweeping up material and then depositing it in a ridge. Now, that's just the atmospheric effect. Now, if we add water, then we add something else again. We add a lubricant. We add the possibility that once that material hits the ground, it'll flow. We add the possibility that the sizes of the ejecta may be decreased even more. So the laboratory gives us a feel of what may have happened for Mars.
Craters on Mars are not like those on the Moon. But is this because of subsurface ice or a Martian atmosphere? Ron Greeley.
Well, our first indication that something might be different about the Mars cratering record and Martian craters came in 1971 with the Mariner 9 results. In the Mariner 9 pictures, we saw a category of crater that seemed to be characterized by an abrupt termination in the ejecta. Now, these craters, which were called pedestal craters at that time, were thought to be the result of various surface modifying processes. It was thought the ejecta had been eroded back, perhaps by wind. Well, we had a much better idea of what this class of crater looked like when the Viking orbiter results came along in 1976. And we saw this very unusual flow-like lobate pattern to the ejecta. And this was something we hadn't seen at all on the Moon or Mercury. Some of the Martian craters even showed multiple flow lobes of ejecta. Now, the idea was that on Mars, when an impact occurs, a certain amount of the energy goes into heat. If, in fact, there is ground ice present on Mars, this heat surely would melt some of that ice. This would produce a water-charged ejecta, which could, in fact, be ejected from the crater and then be placed on the surface as sort of a slurry-like mixture, which would flow across the surface and in fact, may account for this fluid-like pattern that we see. Well, to at least qualitatively test this idea, we thought what we could do is take and fire experimentally into targets that are viscous.
Which is just what was done, as a matter of fact, into mud.
In this series of pictures, we'll see an impact into a fluidized target. And at this initial stage, we saw the high-speed jetting, sending material out, followed by the phase we see here, which is the main transient crater opening up with the ejecta plume, spreading a deposit eventually across the surface here. Now, in this stage, we see the beginning of a small bulge that's pushed ahead of the main ejecta plume. Now, this bulge is draped across the surface and precedes the deposition of the main ejecta blanket that we see here. In the background, we see rising above the transient bowl a central mound or a central peak. This particular peak rises to a height that is a function of the impact energy that was involved in the impact itself. And so what happens is, as that central peak collapses gravitationally, it sends a surge of material up and out over the rim of the crater and forms yet another ejecta layer. And because the target material is somewhat fluidized, it in fact is relatively free to oscillate as a function of the size of the impact event itself. And so we may in fact produce multiple surges of debris across the surface. The basic question is, could this ejecta pattern be the result of the atmosphere on Mars or the result of volatiles in the regolith? Of course, it could be some combination of those two things. Well, with the icy satellites of the outer planets, we have, in a way, an opportunity to assess which of these two processes might be the more important. That is, we know that there are no atmospheres on the icy satellites, and given their small size, it's unlikely that significant atmospheres were ever present. But we do know that there's a lot of ice within the crust of those objects. And so if we saw ejecta patterns similar to these that we see on Mars, that would suggest that volatiles within the crust is the more important process.
1977 saw the start of a mission which would probe the satellites of Jupiter and Saturn. The two Voyager probes were launched then, and 2 years later they were at Jupiter and providing more clues to the history of the solar system. The four largest satellites of Jupiter, Io, Europa, Ganymede, and Callisto, are known as the Galilean satellites. In some ways, they are analogous to the solar system, with Jupiter as their sun. The immense gravitational attraction of Jupiter should have pulled a lot of bodies, such as meteorites, asteroids, and comets, in to cross the orbits of its satellites. It is strange, then, that Io and Europa, the two innermost of the satellites, show virtually no craters at all. Instead, Io was found to be the most volcanically active body in the solar system. Plumes of sulfur dioxide are shot up to as much as 300 kilometers from the surface. This is most likely the result of tidal heating, as Jupiter's strong gravitational field, together with the pull of the other Galilean satellites, distorts the shape of Io, producing internal stresses that melt the interior and cause volcanism. With this large amount of volcanism constantly resurfacing Io, impact craters formed throughout its history are not preserved. The icy surface covering Europa's rocky core must also be relatively young, as only half a dozen impact craters are preserved. But the two outermost of the Galilean satellites, Callisto and Ganymede, tell us rather more about the cratering history of this part of the solar system.
There's one thing that's quite unusual about Callisto, and that is that it has a paucity, or a lack, a deficiency of large craters. That is, craters greater than about 60 kilometers in diameter. There are some large basins that are seen right in here, but generally a heavily cratered surface. Very few large craters. That's the outstanding thing about the cratering record on Callisto relative to the inner solar system, which implies that the origin of the impacting objects and the size distribution of the impacting objects was very different in the Jovian system compared to the terrestrial planets. That indicates another population of impacting bodies which differs quite significantly from what we see in the inner solar system. All right, let's go on and look at Ganymede now. It's quite different from Callisto in that it has these bright bands of relatively young terrain. And we know that because the crater density on these bands is quite low compared to what we see on these darker regions, which must be, therefore, older. Now, if we look at detail of the dark areas, which is shown on this picture, there are these very strange craters here called palimpsests, here and here. They're a bright region with a smooth inner ring, floor, and very subdued rings that you can see here and here. These were initially thought to be the result of a relaxation process in a thermally active crust, in ice. But the evidence seems to be mounting now that these actually form the way we see them. That it's due to the impact process itself in a thermally active crust, rather than a sharp crater forming and then relaxing with time.
So Ron Greeley's question is answered. Craters on Ganymede can be explained in terms of low-strength target material, just as in the case of Mars. And palimpsests, modeled here by an impact into water with a surface layer of wax, may be formed by a jet of volatile-rich ejecta from the crust falling back and spreading on the surface. The volatiles, not the atmosphere, are the key. But surfaces like these tell us much more than just what the satellite's composed of. The distribution of craters on their uneroded surfaces tell us about the formation of the solar system itself. The distribution of craters on any surface, once you allow for erosion and resurfacing, is directly the result of the number and size distribution of the bodies that impacted into it. For the inner solar system, two distinct cratering populations have been identified. For example, on the Moon, we have the highland population, over 4 billion years old, and the younger population preserved on the lunar Maria. But on Callisto and Ganymede, we find a new population not seen in the inner solar system. Where is it from? A partial answer to that question comes from the satellites of Saturn, which tell us more about the cratering record of the solar system.
these satellites, aside from Titan, are all quite small compared to what we've been seeing in the Galilean satellites. These are bodies that, in the case of Mimas here, that's only about 400 kilometers in diameter. There is a rather large crater here. Not much larger in impact would be sufficient to almost totally blast the satellite into smithereens, basically. All right, let's look at another peculiar one, which is Enceladus. And Enceladus, in many respects, looks like Ganymede. We see these kind of this grooving. We see areas that are very lightly cratered and others that are fairly heavily cratered in here. So we can tell from this, just from looking at the cratering record here, that there are areas that are quite young and have been resurfaced by some type of volcanism, and other areas that are older. Now, it's on these cratered areas here on Enceladus and other resurfaced areas that we see this younger population. It has a different signature in the sense that its size-frequency distribution is different than what we see in the heavily cratered regions of these Saturnian satellites. Now, let's go to another one. This is the satellite Tethys, which is about 1,000 kilometers in diameter. It's characterized by a very high abundance of small craters and a dearth of large craters, somewhat similar to what we see on Callisto and Ganymede. Now, remember I stated that these are all very small bodies, so it wouldn't take a very large impact to completely disrupt a satellite. And a good candidate for that disrupted satellite is this very odd-looking body called Hyperion. This is our highest resolution picture of it. It's not the greatest, but this is an oddball. And as you can well see, it's not even round, all right? It's very irregular in shape. Not only that, it has a fairly low albedo. It's fairly dark. And finally, it has an odd motion. It is not in synchronous rotation. It could be that the reason it's not in synchronous rotation and the reasons for its irregularity and for its low albedo is that this is the source of the fragments to account for this early population. In other words, it was hit by an object large enough to almost completely disrupt the entire satellite, and all that remains is a kind of an irregular core left over from that disruption. So what we're confronted with when we look at this in a general way is that there appears to be on the order of 5 different crater populations, 2 of which are indigenous to the inner solar system, 1 indigenous to the Jovian system, that is Jupiter, and 2 that are indigenous to the Saturnian system. So they appear, in the case of the outer planets, the impacting objects appear to originate at the planet in which they are found, possibly accretional objects or disrupted satellites in that cases. In the inner solar system, where we see the same crater population represented in all the heavily cratered regions, that could be accretional remnants. That is, objects left over from the accretion of the planets themselves.